Good afternoon. Welcome to today's SCA webinar with Dr. Leslie Wood on exploring in ancient landscapes seismic geomorphology. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. And so I'm going to share some polling questions. The first question is, what's your primary discipline? So we're starting to get responses. We have some geoscientists in the audience. In fact, a significant percentage of you are geoscientists. We're still getting some responses as people are logging into the call. Okay, well, at this point, 3/4 of you have voted on your primary discipline in the GoToMeeting tool, and all of you, 100%, are geoscientists. So that's pretty remarkable. I'm going to share those results. I may be the only petroleum engineer on the call. So let's go to the next question. How many years of full-time experience do you have in the upstream oil and gas industry? Quite a few of you have over 30 years experience, but we have some in the other categories as well. We're starting to get responses. Still collecting the votes using the GoToWebinar tool. Please tell us how many years of full-time experience you have in the upstream oil and gas industry. So at this point, the votes are still coming in, but 40% of you have over 30 years experience, and 30% of you are in the 21 to 30 year range. 20% of you are in the 1 to 10 year range, and 10% are in the 11 to 20 year range. I'm going to go ahead and close the poll, share the results. Most of you have voted, so thanks for your responses. Before I introduce Leslie, I'd like to remind you that you will be muted in today's webinar. And so if you're going to be asking questions, you can use the GoToWebinar question feature, and we'll cover the Q&A at the end of the presentation, and you will be anonymous. So welcome to today's webinar on exploring in ancient landscapes seismic geomorphology. Dr. Leslie Wood is our speaker today, and Dr. Wood has a very illustrious career. You can see she's currently on faculty at Colorado School of Mines, where she holds a Robert Weimer Endowed Chair in Sedimentary and Petroleum Geology. She's also the director of the Sedimentary Analogs Database and Research Program. She also held positions at the University of Texas at Austin, Amoco, and ARCO. She received her doctorate from Colorado State and has done work in a number of disciplines. She has a long career of leadership in several of the professional societies. I know she's very well published and has won numerous awards. Most recently, she was recognized in 2022 with the APG Berg Outstanding Research Award, and the Society for Sedimentary Geology elected Dr. Wood as an honorary member. Congratulations. So seismic geomorphology is a class that Dr. Wood teaches for SCA. It will be offered in Houston, Texas in February. You can see the class description is listed here. Lots of information, and you can find a link online. I want to remind you that we have some upcoming classes that are offered in live online format. In the next few months, we have carbon capture, utilization, and storage, an engineer's perspective with Dr. Christine Ilig-Economides and Dr. Demetrios Hazignatu. That's offered November 14th through 18th in the mornings. We have 2 classes that are offered by Srini Prasad, maximizing upstream oil and gas exploitation values and developing robust production forecasts. Those are both offered in January in half-day formats. And Bob Barbet is teaching best practices for new well fracs and legacy well refracs. That's also offered in January at the end of the month. We have several webinars that are scheduled in the near future. The next one is in December 8th. We have Everton Arujo speaking on the geomechanics of carbon capture sequestration. And in January, we have Furman Fernandez speaking on excess permeability in carbonate reservoirs, curse or blessing. And of course, you can bring SCA's training courses to your in-house location. So contact our training department for more information about that. And in addition to training, SCA also provides consulting, direct hire services for both contract and full-time. We do projects and studies as well. So I'm going to hand the presentation rights over to Leslie. And it's all yours. Take it away.
Awesome. Thanks, Susan. I appreciate that. And I appreciate the opportunity to be here. So you guys, I'm sure I know many of you. I haven't seen a list of names, but those of you who are 30 years plus in the industry, you came up in the industry in the 90s. And so that was when sort of seismic geomorphology and the ideas of sequence stratigraphy were really just being applied. In the other attendees progressively were coming up in the 2000s. We didn't publish the first real book in seismic geomorphology until the 2000s when Richard Davies called me and said, hey, you want to co-author this conference and this book. We had the conference in Houston, and it was on seismic geomorphology, and so there's been a lot of publications since. But I think today what I want to talk to you a little bit about is the class that I'm talking about teaching, and then I want to talk to you a little bit about why seismic geomorphology may be a tool that you want to put in your toolkit. So let's cut right to it. Yeah. So well, I can get back to where I'm going here. Oh, see, I'm just not adept at, well, any of my students will tell you I'm not adept at technology, but I got this out of the way. Let me get this up there. So I appreciate the opportunity from SCA to come to you guys. Seismic geomorphology, I've figured out over the years, it's not really an end-all be-all. It's a tool that you have in your toolkit. And it's really about mapping and understanding paleo landscapes, paleo seascapes, and something I've been talking about, which is accommodation scape. And so we're going to talk about some of that here briefly. The class itself, I talked to SCA about whether to teach it online or teach it face-to-face. We decided to offer it face-to-face for 3 days at the end of February. And then we'll look into offering it again online for some of our international audiences or people. I like the face-to-face format just because it facilitates, I don't have to tell you, it facilitates more conversation and more interaction with exercises that we're trying to do. And really it's the exercises that I think are at the heart of a lot of what I do in this class. So the opportunity to really talk about how you take techniques and apply them. We're going to learn techniques in mapping seismic geomorphology, but also in how to use well data and log data to understand the three-dimensionality of reservoirs and seals. We're going to talk about how to interrogate our data with methods that allow us to maximize the imaging of basins geomorphic systems. We're going to talk about our knowledge of seismic expression of and how we recognize plan form and cross-section varieties of various elements in depositional systems. We're going to talk about how fluid flow happens in that basin in and around those geomorphic elements and in and around that accommodation scape. And then we're also going to talk about interpreting and using and calculating process and quantification of implications for data assessment for decision making, because that's ultimately what we're trying to get at, is how do we use this new tool and how do we use the information we glean from it for decision making. The first day of the class, we'll go into fluvial systems, We'll do some exercises using core to go from simple two-dimensional point bars and two-dimensional bed forms and dune forms into three-dimensionality of river systems and channel systems. We're also going to talk about deltas and shelf edge systems and the shelf on the first day of the class. As we move more into carbon sequestration and depleted reservoirs, we're going to have to turn ourselves back to some of our shelfal systems. We've been playing around in deep water for a lot of years, digging around for things like Lisa. But even ExxonMobil and other companies recognize that, the playground for carbon sequestration and things these days is in these shelf reservoirs. So we're going to learn more about the shelf. Day 2, we're going to move off the slope and talk about toe of slope processes and deep water processes. You're going to get to see some unique data from offshore Guyana through the Berbice Canyon system. This is a project that we did a couple of years ago in collaboration with Repsol. And we're going to look at some of that data and use that data to talk about canyons and valleys. And then we're going to talk about mapping complexes, channel complexes in offshore Gabon. Finally, on the third day, after reviewing the Gabon exercise, we're going to dive into lobes, both frontal and lateral deep water lobes. And then we're going to get into the heart of a real strong interest of mine in the past several years, which is mass failure processes and properties, and mass failures in exploration, production, and in carbon sequestration. So we're going to talk about the sealing capacity of mass transport deposits. We're going to talk about how to use seismic geomorphology and well data and things to sort of interpret the morphic character and the physical properties and the structural properties and mechanical properties of these types of mass failure deposits, because they play such an important role in deep water systems. Then we're going to talk a little bit about deep water continuous current systems. Some really great work that's been done by some of my PhD students in both of those two topics. And then we'll wrap up day 3 by talking a little bit about geotechnical assessments and carbon sequestration assessments and how we can use seismic geomorphology and geomorphic approaches to working and understanding in those type of settings and questions. So why would you even care about this tool? Well, landscapes and seascapes form the foundation upon which all sediment accumulates. I mean, you can see here, this is the Grand Canyon, and there is no better representation of the accommodation that sits for an incised canyon or valley than the Grand Canyon. If we look at landscapes and seascapes, they've fascinated us all, especially people that have a geoscience background, for millennia. Right, and Captain Smith was on the Beagle when it was sailing, with Charles Darwin, and he spent his entire cruise, for months, even years, just mapping and sketching different types of environments, different types of depositional features, different types of landscapes. Here he's caught the sedimentary rocks and their relationship to the igneous rocks that sit. So this is really great conformity sitting in here, on the Isle of Cyclops in the Bay of Teresa. And so we've had this love affair with landscapes for long periods of time. As I said today, we've got to be able to map the foundation upon which sediments erode and are transported and are deposited if we're to understand their nature and the distribution of their morphology. The Grand Canyon represents this great accommodation environment where eventually it's going to fill with an amazing valley fill. And I remember looking at this and thinking how complex it was, and how if I were exploring in this type of environment, how would I even begin to look within this type of complex environment for the types of sediment flows and fluvial deposits, and even if it were in a submarine environment, gravity flows interacting with this type of complex topography. And this got me to thinking about accommodation and accommodation escapes. Accommodation, its definition of accommodation is making room to allow something to happen, and we certainly have that room in these type of environments. But escape denotes a specific scene, like a seascape or a landscape or a moonscape. And so when I talk about accommodation scapes, I'm really talking about the nature of a scene that allows sediment to move across it and to collect in that space. And that's a more complex idea than just saying, I have this volume of accommodation and I'm going to fill it with this volume of sediment. Because understanding the accommodation scape, the different slopes, the different barriers, the different obstructive features, and the way the architecture of the actual accommodation scape is generated and expresses itself, understanding that allows us to think about process sedimentology and how gravity flows in a submarine environment or flow in a subaerial environment would interact with that accommodation scape to collect sediment within that space. And so that's what I've been turning myself and a lot of my students toward, is to looking at mirroring the nature of the foundation upon which the sediments are deposited and the processes that move and deposit the sediments and how it interacts with that foundational feature. We've really made quite a lot of advances. In the first 100 years of paleo landscape mapping, we looked at a lot of modern environments, and balloon travel helped us a lot. And then, of course, the ability to fly aerially over areas helped us be able to visualize things like distributary channels and levees and crevasses and overbank deposits, right? We turned this into some form of these deposits. And the things that we had to go on were well logs and core and things. So here we have our distributary channel, we have our crevasse splays, we have our levee systems, right? But it really took a step up whenever we began to develop 3D seismic. So our ability to image and study landforms and seismic data became the science of seismic geomorphology in the 1990s. And I remember at that time I was working with Kurt Marfort, and Mike Bohoric was actually working out in Denver, and he was developing this tool to look at discontinuity in seismic data. And so we were developing new ways in seismic data to image discontinuity, to map faults, and for me to image discontinuity to map the edges of depositional systems. And so when I was with Amoco Production Company, I had the good graces to work with Greg Partika and Kurt Marfort and others to sort of begin to interpret these seismic images using seismic, the new science of seismic geomorphology. Seismic geomorphology is the study, and this became a tool in my toolkit, right? So I knew how to do basic stratigraphic mapping. I knew how to do well log analysis. I had petrophysicists, I had petrographers, but this, as well as, sequence stratigraphy and this science, began to teach me how they were new tools in my toolkit. And that's really what all this is. And the more tools you have in your toolkit, the more likely you are to have a correct answer or a low uncertainty answer. Seismic geomorphology, as Henry suggested, is the study of landforms and depositional systems using 3D seismic images. For me, having a geomorphology background, I knew that we could quantify these landforms and we could quantify the history and the processes and the nature of the fill within them and the architecture of the fill within the basins if we could just map them and quantify their architecture, calculate their sinuosities, look at their width to depth, look at their width to depth ratios, look at the size and the different features that exist. And so that's what I kind of launched into doing. A good example of this large scale landscape formation is a piece of work that we'll talk about, but that we did in the Jurassic Mountains. I call them the Jurassic Mountains of the Northwest Australian Shelf. A really good postdoc of mine, Chin, and a good friend of mine, Rob Galthorpe, and I were working this data provided by Woodside a couple of years ago. And what we did was we wanted to see, could we come into this data and could we actually calculate and look at the drainage area or the foundational landscape across which the sediment was being derived, and then the shape and the nature of the depositional basin, and how did the footwall fans and their architecture relate to the drainage basins. And so Chin began to look at, and this is a cross section simply taken across there, he began to look at the catchment area links and the boundaries of the watersheds. And if we could map the catchment area and the boundaries of the watersheds, we felt like we could come off into the footwall fans and say something about them. And so Heha did a super nice job of simply utilizing the details of the topography that he was mapping along the unconformity surface and defining several drainage basins. Those drainage basins, the Dixon, the Goodwin, the Perseus, the North Rankin, the Eagle Hawk, the Lambert, we felt like we could go in and take some size and space area within these drainages separated by the yellow lines, and we could calculate the size of footwall fans. Well, when we did that, we noticed that there was a southern suite of footwall fans and there was a northern suite of footwall fans in drainage areas. And the northern areas seem to be unusually large if we looked at catchment area versus fan area. And the southern areas seem to be smaller compared to catchment area to fan area. And so when we looked seismic geomorphologically at the images that we could collect down this area, we could see these erosional features that were happening within the deeper part of the footwall. And they were lineations within the seismic data that were telling us that there were geomorphic processes that were going on in the deeper part of the footwall subaqueously that were toe trimming the fans to the south, and they were redistributing those sediments in the fans to the north. And that's why we were seeing these unusually large fans for the size of the catchment areas compared to the other fans. So that type of toe trimming process we've seen happen in other environments. This is an example from another paper that Chen has done, where you can see these very non-trimmed fan systems. And then you can see that when you get into an aqueous environment, you begin to trim these fans and move these sediments in a distributed downstream direction. So this was a way for us to look at how the processes were interacting with the topography in this accommodation scape environment, and began to see how that was interacting to redistribute sediments within this larger environment. So these are sort of large-scale geomorphic principles and ideas that we can interpret and apply to our seismic data. Likewise, quantitative seismic geomorphology is also about predicting the nature of the deposits. So in other words, it's not enough just to predict the volume of the footwall fans or predict the volume or size of river systems. But what we want to do is we want to understand what are the sediment types, what's the spatial distribution, and what's the architecture, and potentially what's the sedimentology and architecture, and what are the petrophysics of some of these deposits. So based on the premise that form denotes process, process denotes the sediment types, spatial distribution, architecture, sedimentology, and petrophysics. So we can take quantitative approaches like measuring channel widths, measuring radiuses of curvature, meander lengths, sinuosity, meander welts, and we can begin to calculate some of these architectures even in ancient systems and use that information. One of the better places that I started doing this was in the West Natuna Basin in Indonesia. This was an amazing set of data provided by ConocoPhillips Indonesia and the Indonesian government. The data itself is called Gabus and Bolonic areas in the West Natuna Basin. There are multiple phases in this basin of sort of extension and compression. There's about 13 wells that came along with the data set, so we're always integrating well penetrations when we can. Every one of these slices, and I'm just going to run it for you again, every one of these slices I'm going to say characterize about 10,000 years of time within this system. And you can see the incredible data, the incredible detail that we have in imaging these types of systems, but every slice represents 10,000 years time. So we talk in this class that I'm going to teach about some methodologies for how you can, sort of parse the chaos out of this data set and make some sense of interpreting salient or important features in here that can really characterize, quantify the nature of fluvial systems within each one of those 10,000 year slices and some of the important processes that the data reflects. So some of the work that we did within this data set included just looking at reservoir size, shape, and orientation. We went and we quantified, here's a histogram of channel widths that are just taken, from a compilation of information within this basin. You can see this miles, several hundreds of channels that we measured. It's enough to, if this is enough for your basin, you can go through and do a quantitative probability analysis for looking at the cumulative probability of certain channels. The P50 of channels within this basin is about 400 meters wide, 200, 300 meters wide. So you can go in and do this type of cumulative probability analysis. You can get an architectural suite of channel systems, or you can take this a step further and parse the basin into important phases of evolution within the basin. Some long-term trends in basin fluviomorphology show that there's a cyclicity in sinuosity that occurs within the basin, right? And that sinuosity within the channel systems is on average very different whether you're in the post-rift phase of the basin, the sin inversion phase of the basin, or the post-inversion phase of the basin's development. The other thing we noticed was when we went in and we began to measure the main axial orientation of the channel systems, if I was in the post-rift phase of the basin, the channels were oriented northwest to southeast as a function of extension, pulling the basin apart. As I began to go into sin inversion, I began to mix my channel systems much more in terms of their orientation. And then finally, when I got into the post-inversion Muda formation, we see those channel system orientations shift completely to northeast to southwest, almost 90 degrees. So if you're trying to produce this and inject and produce out of this type of environment, in this case gas resources, then you need to know what the dominant orientation of your channel systems are, and you can find this by mapping them geomorphologically. You can also see that whether you're in the post-rift, sin-rift, or post-inversion phase of the basin, it has an effect on the channel width. So in the hundreds of channels that we measured, we could see that the smallest channels were in the post-rift phase, oriented northwest to southeast, I guess. Oh no, oriented northeast to southwest. And then the largest channels are actually in the post-inversion phase, the more younger channel systems, but they're almost twice as large as the early channel systems. So this gives you a chance, you can actually plot a chance of finding a reservoir of a certain size under different tectonic regimes using seismic geomorphologic approaches. Finally, if you're really wanting to dig into an engineering perspective of what these channel systems look like, then you can go in with some of these really nicely imaged channels. This is done by a graduate student of mine, Brian Kyle, and he mapped this channel shape, and it's really great for identifying places in the channel where you have deep scour occurring in the base of the channel system. And these deep scours have implications for how fluids are produced out of these channel systems. The other thing you can see if you don't have this beautiful deep image is, we try to define larger objectives in here, which is, these scours are occurring in very predictive places. They're occurring in places where you narrow the overall width of the channel, you narrow the overall width of the channel, you increase the flow, and you come in, and that happens when you're coming into a bend. So if I had to predict for you just based on plan form, I could draw you circles where I think you will begin to get these deep, potentially deep scours occurring in your channel system. And it allows you to plan in advance for those type of things. These are some of the approaches that you can take to applying geomorphology to larger scale issues of reservoir presence and sediment supply, and smaller scale issues of reservoir characterization. We do seismic geomorphology, we'll talk about a variety of different types of environments, not just siliciclastic environments, but also carbonate environments. This happens to be an image from the Permian shoreline evolution in the Permian Basin. And here you can see patch reefs and multiple shoreline advances as the shoreline is moving. I'll do that again, from left or west to east to its final location at the shelf margin out here. And within this framework, you can see patch reefs, You can see tide-dominated inlets and tidal inlets, as well as shelf subaqueous channels and things that are feeding sediments out to the shelf edge. And then, of course, the distal shelf and the slope out in here. So we work at siliciclastics as well as carbonate environments. We work in shallow and deep water environments. This is an image from some Albion deep water sediment waves that are they're oriented northwest to southwest to northeast, and they're deposited prior to salt intrusions. We can tell that because the salt intrusions don't seem to affect the occurrence or the orientation of these channels, of these deep striated sort of deposits, or these are what people would call contorites or drifts. These are albionades. This is an amplitude extraction. And you can see how they extend across the entire Safi-Hot Mer or Moroccan offshore area. The salt bodies are shown in red. So Dallas Dunlap and I and other members of our team did a lot of work out here and mapping the Chad Westenberger, I think, mapped the salt, and we were mapping the geomorphology of the system. These features are not unusual in deep water environments. We're all beginning to learn a lot more about them after the good work from the drifters and our own sedimentary analogs database group. Don Beelan has been doing a lot of work on these systems. So if you want a visual, these are probably very similar to these extremely large, Barcan and sort of types of dune systems that you see in onshore systems in different parts of the world. So we'll talk a lot about those deep water. I call them continuous current deposit wave fields. Some of these are kilometers high, or 100 meters high and kilometers long. So the other thing we talk about is how we use this data. This is some work done by Zane Jobe and some of his students and his postdoc at Colorado School of Mines. Zane and I work very closely together, and he's come in and collected a variety. We collect a variety of quantitative data sets, and we use these to inform how we condition numerical models. The SG data also provides insights into risk and uncertainty. Mass transport deposits, we can see, we have tools that we built, such as this by Sebastian Cardona, to risk the seal properties of mass failures. We have geophysical insights into these seal and no seal mass failures. We will also go through and talk about how we can use things such as the size of clasts and rafted blocks to calculate the yield strength of mass failures. Yield strength is maximum shear stress a material can withstand before it begins to deform plastically. And we can take the weight of the largest class that's transported by the flows, which we map geomorphology through seismic geomorphology, and we calculate the buoyant force and the matrix strength. And we can look at the yield strength of these types of deposit and begin to understand what is the sealing capacity or the shear strength of some of this material. This works not only for seal character of some of these deposits, but also works well for looking at some of the hazards issues of how you drill through these, which I know a lot of your companies are trying to deal with. So we're trying to get at some of the geotechnical issues that surround these types of deposits. Finally, we will probably talk briefly about forms denoting process even on other planets. This happens to be a piece of work from the Eberswald Delta on Mars. So I do planetary landscape analysis, and a lot of this type of work sneaks into conversations that we have about process and how we interpret these types of forms in seismic data, because I find Mars to be a really good example of how you can't put boots on the ground and you can't actually core something, but at least you have some seismic data that you can image form and by form calculate process. So where we can, we like to integrate logs and core together with seismic data in this seismic geomorphology class. But where we can't, we're going to come up with some methodologies to utilize this type of approach in seismic only basins as well. So I hope that you guys can come into the class. It's going to be a good 3 days. We're going to talk about and have several good learning outcomes. And my goal in this class is to have some very applied outcomes come to people who are involved in this class and taking this class, because I want you to take some of these methods from my toolbox back into your own toolbox and apply them in your own basins to better understand things like reservoir presence and absence, seal quality, sort of the petrophysics and the sedimentology of systems, reservoir pathways, various things like that, and even geohazards and carbon and sequestering carbon in types of environments like this. So I thank SCA, and I also thank some really great colleagues that I've worked very closely with over the years, as well as the immense amount of companies that provide the data that you've seen here and some of the data that you're going to see in the class in February. So with that, I am happy to answer any questions. I'm going to turn this back over to Susan. So
thank you for the presentation. And I want to remind our audience that you're muted, but you can ask questions using the GoToWebinar question feature, and I'll be happy to relay your questions. After today's webinar, you will receive a link to a recording of today's webinar in case you want to share it with your colleagues. You'll get an evaluation form and a link to register for Leslie's course on seismic geomorphology that's scheduled for February 13th through 15th in Houston, Texas. And Leslie also teaches the following. Sorry?
No, go ahead. Go ahead, Susan.
Okay. Leslie also teaches the following courses: Deep Water Deposits Field Course. That's in Arkansas and Oklahoma. It's a 3-day field trip. And the Reservoir Characterization of Clastic Sandstone Reservoirs. That's a 5-day class. So contact SCA's training department at training@scacompanies.com to an in-house course of either of those two offerings. And so you mentioned that accommodation scape was a phrase that you talked about in your presentation, and you said different scenes allow something to happen. So which are the scenes that allow the most accommodation to take place?
Well, the place that would build the most accommodation would be to bypass an accommodation entirely, right? But that's not the idea. That's not what we want to do. I think when I've begun to, like I said, I've begun to formulate and talk about this idea of accommodation scape, because as I look at these areas of accommodation, whether that's an incised valley like the Berbice Canyon, and what's interesting about the Berbice Canyon in offshore Guyana is that it erodes 1,200 meters and then it fills up, and then it erodes again 1,200 meters and then it fills up. And so not only is it fascinating that the northern continent, the northern part of South America is pumping out this enormous volume of sediment, but I began to think about, as we mapped those different phases of fill, each one that was older than the other formed the foundation for the next phase of sediments to be supplied. So every envelope of accommodation within that evolving Berbice Canyon, it had a different look and it had a different form. And so we had to map each one of those, because the initial container was not the accommodation that each phase of that sedimentation was interacting with. Sometimes those containers, those interim containers, were much more complex, much like we see today in the Grand Canyon. And so it was important to think about, what were the slopes? What were the barriers? Was it full of hoodoos of older Cretaceous sediment, or these sort of uplifts of older Cretaceous sediment? Was it focusing, channel systems and river systems and deltas? Was it, so how were the sedimentary systems interacting with that landscape in order to produce that fill? And that's what I refer to as the accommodation scape of a certain place on the planet. Now, ultimately, the ocean seafloor has more accommodation than it knows what to do with, right? We are probably never going to erode to where we fill up the Atlantic seafloor. We've just not done that since Jurassic time, right? It's just opened and closed and opened and closed, and we're continually sort of filling it back up. So the ocean seafloor may have the ultimate accommodation, but that's not, and you make a good point, which is it's not only about accommodation, it's about how do we fill it with optimal sediment that we want to see, right? And so we need to find those areas where we have great accommodation, maybe low complexity in the accommodation surface, but an opportunity for sediments to shed within and fill that accommodation. Now, what has happened in the Guyana-Berbice area is there are places within that Berbice Canyon which it's provided bypass out into the deep ocean area where the Liza or the Liza and all its sisters now sit and reside out there for ExxonMobil. So I want people to start thinking about not just the hole we're filling, but how the sedimentary processes are interacting with the shape and the nature of that hole to either accommodate sediments or to move sediments basinward.
Thanks. Next question, what is the strategy for attribute extraction? Rather than time slices, would it not be better to create GIS maps and then slice through this volume? And the questioner lists the reference of Bush 71.
Huh. Bush 71. Wow. I'm gonna have to go back and find that.
Look for that one.
1971. We do a huge amount with GIS here. And we use it a lot to layer over just different layers of attributes and things. I don't use, I know that I have some colleagues that use GIS to interrogate and pull up images. We did have a project where we actually loaded data into ArcGIS, and we used ArcGIS to do that and interrogate the data. And I want to.
The questioner has provided some additional data in
Okay.
GIS, referring to genetic increment of strata, not the software.
Oh, I thought you meant geographic information systems. Genetic increments of strata. I'm going to tell you, I'm going to have to go look that one up. Tell them to provide some more information.
I'll do that.
So Bush 1971, I just want to clarify, is Bush 1971 a paper that talks about genetic increments of strata?
It's B-U-S-C-H, Bush.
Okay.
It appears to be the author, and it's referring to genetic increments of strata, yes.
Huh.
Maps
I don't know. I'm gonna have to look that one up.
An APG memoir.
Say that again.
It's an APG's.
Oh, APG memoir. Okay. So APG in 1971 would have been about the time that all the Exxon guys were pouring their heart and soul into sequence stratigraphy. And there were certainly individuals who were coming up with alternatives to alternative names and alternative approaches to looking at forms and functions. I'm going to have to go look that reference up. I appreciate that. Actually, you're coming up with a you're coming up with one of the reasons that I like teaching these classes, because
you always learn something.
Yeah, you guys come up with ideas and references and things that I don't know about, and so it offers me an opportunity to broaden my understanding or broaden my own toolkit or my perspective on things. So I say I'm going to have to go back and take a look at the genetic increments of strata. If you want to, whoever this is, I'm pretty easy to find. You can find me, at elwood@mines.edu.
Reference stratigraphic traps and sandstones exploration techniques by Daniel Bush, the 1974 edition.
I'll look and see, because there's going to be somebody, if he's out there, that knows him. But it gives me an opportunity to go back and look at some things grab some things and read some things. So I appreciate that.
Question. Talk a little bit more about the redistribution of sediments through toe trimming.
Through what?
The toe trimming process. You were
the toe trimming process. Yes. So I was looking at this 3D data I have been looking at this 3D data in the Dampier Subbasin, both when I was over in Woodside's offices in Australia with Dallas Dunlap, my colleague, and then also after we got it and we were using it to do some stuff here at Colorado School of Mines. And you could see very clearly, in that footwall of that basin, you could see that there were processes going on that were sort of moving sediments back and forth in the very deepest part of that footwall. There were these lineations, and I could not figure out, and I did figure out that those lineations were destructive, right? So they were erosional, and they were cutting these little trenches. It's almost like a moat that's happening at the foot of a toe of slope. And you know, Don Stowe and those guys who study currents and things, they talk about moats at the base of the toe of slope. But that's what this was. It was almost like a moat or something. And then Rob Galthorpe showed an example from the Gulf of Corinth, where he had turbidites that were originating in the head of the Gulf of Corinth, and they were sweeping down the Gulf of Corinth, and they were actually trimming off these fans that were coming from the margins along the Gulf of Corinth. And of course, the Gulf of Corinth is a rifted basin, right? And so then Heche was also seeing the same thing in these subaerial pictures that I showed you, where you're toe trimming off those fans. And this was all, I mean, coming at this process was actually driven by the observations that the fans to the north were overly large compared to their drainage areas, and the fans to the south were overly small compared to their drainage areas. So a project that I'm trying to get a master's student to take on right now is, now that we think that the fans to the south are toe trimmed and the fans to the north are overly large, how does that change the architecture of the footwall fans? They were subaqueous, and they were sitting down on the margin of this rift basin. And so I want a master's student to go back and look at each of those 6 fans and compare and contrast their their internal sort of architecture and morphology and their sedimentology, because they have cores through them and they have well logs through them. And so, which will unfortunately necessitate another trip to Perth, but I'll just have to do it. So to see, you know, well, now that we think we have an understanding of the process that's causing this differential between the northern and southern fans, and we see this in the Gulf of Corinth and we see this in China, it's like, how can we go in now and sort of talk about the implications for reservoir, seal, fluid flow, you know, quality, things like that. So it's always a work in progress. Like every time you answer some questions, you come up with more questions. But
absolutely.
Yeah.
So in the Natuna data set, you were showing the different sinuosity and the different time slices. What causes the orientation changes, and can you predict that?
Yeah. So what causes the orientation change is the West Natuna Basin goes through this phase. I have to figure out how to do this. The West Natuna Basin goes through this phase where it's extensional and it's oriented, and those valleys are oriented northeast to southwest. And then you remember your long plate boundaries, and so you're rotating plates, and you get this situation where these plates are rotating, they become compressional. And so the West Natuna Basin closes up and becomes compressional. And when it becomes compressional, then you're controlled by the orientation of the compressions, right? The compressional fold axes. And so those compressional fold axes mean that, you know, just like in the front of the Rocky Mountains, those compressional fold axes give us channel systems that are, you know, that are rolling sort of northwest to southeast. So we go from extensional channels, where the channels are coming through there and they're actually, you know, northeast to southwest. And then in a later phase in the basin, it becomes compressional, and the compressional features are northwest to southeast. So that's what causes the shift in orientation. So in that case, the larger drainage system of the West Natuna Basin is very closely aligned with the tectonic phases of the evolution of the basin.
And were some of those channels slicing through all those different time periods?
Yeah, so so what you're looking at when you look at one of those 10,000 year slices is you're looking at a drainage system, and it's composed of individual channels. Every one of those individual channels may persist for longer than you would expect a single channel to typically persist for, because they're controlled by structural orientation, right? So in effect, they're trapped along structural faults. So they stay in a certain orientation for a much longer period of time than you would think. Most channels last for a very short period of time, right? And then they're moving and they're migrating and they're going back and forth. But I think that what you'll see in the West Natuta Basin is that you have these fairways of channelization that persist for 100,000 years or something, but the individual channels within those fairways may only persist for 10,000 years or something.
And the orientation change doesn't cause those fairways to change direction?
Yeah, it causes those fairways to change direction, but you know, the bigger question is, how does that transition happen? We're all caught up in transitions now, but we've, you know, understanding how you transition from a system that's going sort of northeast southwest to one that's going northwest southeast. It's like the big question marks that's in this space right here, right? It's like, does that transition happen really suddenly? How is that transition reflected in the morphology of the channel systems? You know, some people might say, oh, it's that period of time when it looks really swampy and you have a lot of coals and you have a lot of sort of anastomosing channel systems, when the channel systems are really trying to reorganize themselves. And that period of reorganization, you know, may take 20,000 years, and you get this period of sort of high anastomosing, really poor reservoir, really confused orientations. You can kind of see that in that sin inversion time period. If you look at the channel orientations in the Bolonic area and the Gabus area, they no longer make sense with one another. You know, in the early phase, the Gabus and the Bolonic areas, the channels were all oriented northeast to southwest in both areas. And then in the post-inversion, the channels were all oriented northwest to southeast in both areas. But in the sin inversion, in that time in between, the Bolanic channels are oriented one direction, the Gabus channels are kind of oriented in another direction. There's a lot more spread to the channel orientations. So that's a very good question. And you know, I think the confusion in the system may range more in that when it shifts over, and you know, it's reflected as a lot of confusion in the system.
They have a lot to learn, I'm sure.
Oh, there's a lot to learn.
One question, talk about scouring and the importance of understanding the scouring impact as you're doing geomorphology.
I've come to appreciate scouring a lot more since Sebastian Cardona, one of our students, began working mass transport deposits. In mass transport deposits, scouring is actually, it controls how much you erode and incorporate material from the underlying units, the underlying beds, right? So scour does a lot of things. Scour, the amount of scour that you see can put you in contact with underlying units that you know, that actually intersect your, you know, your channel systems, and your channel system will either seal material in that unit, or it will allow material to leak into the channel system. Scour has had an effect like that in some deep water systems in offshore Gulf of Mexico. There are fields where everyone was drilling the channels and they were all mud filled, and no one could figure out that they were scouring deep enough that they were actually sealing all of the crevasse splays and things that were holding hydrocarbon around the channel systems. So I think one of the companies drilled like 5 dry holes before they figured out that they actually need to be looking at the scour as a seal. Companies are beginning to ask these days, what's the probability that mass failures will seal underlying material? And that has to do with the depth of scour and how much the scour is incorporating sandy material from underneath it. So the biggest scour and the biggest erosion thing I literally have seen is the Berbice Canyon area, not just its individual scour and erosion, of 1,200 meters or 1,700 meters. But the fact that it has multiple surfaces of erosion to that degree. So the total volume of material that was excavated out and moved basinward in that system is enormous. And I mean, you're seeing it today in the reservoirs that sit and exist out in the Guyana, Suriname area, right? So scour on a really massive scale, erosion, plays a critical role in reactivating sort of, dormant sedimentary accommodation scapes and moving sediments basinward into more basinward depot centers where they're more closely in contact with source rocks and source rock areas. And then it plays an incredibly important role just on the engineering scale of understanding how those scours are impacting fluid flow as it's happening between depositional elements within a single field or across a single field area.
Sounds like a great tool to use in exploration.
So we're going to talk about how we can take the plan form of a morphic element, even a channel system, and how we can begin to, based upon the morphology of that system, how we can predict the three-dimensionality, including the scour depth of some of these features. So
very good. Well, that's all the questions we've received from our audience today. So I want to remind everyone you'll receive a link to a recording of today's webinar, an evaluation form, and a link to register for the course on seismic geomorphology that Dr. Wood teaches for SCA February 13th through 15th in Houston, Texas.
Yeah, thank you guys.
Dr. Wood also teaches the following courses: Deep Water Deposits Field Course through Arkansas and Oklahoma, and the Reservoir Characterization of Clastic Sandstone Reservoirs. That's a 5-day course taught in Houston Training Department. So contact SCA's training department at training@scacompanies.com to schedule an in-house course today. Thank you very much for your time. Goodbye.
Thanks a lot, guys.
Bye.
Bye.